Sounds good. All right. Well, thank you all for coming. We are NASA's Break the Ice Lunar Challenge. We are the representatives from the excavation sub-team as well as track design. My name is Tom Neumeister.
My name is Dante Terabelsi.
My name is Ben Lawaji.
My name is Tate Mueller.
So yeah, I'm just going to give a little background on NASA Break the Ice Lunar Challenge. This is a 2-year-old project, and it kind of started with the idea of making the moon a gas station for us to get to Mars. And for our specific challenge, our purpose is to get water from under the moon's surface, specifically a crater on the south pole of the moon. And we need to be excavating icy regolith from below there, transporting it 500 meters to the dump site where the regolith will become water. And then from there to the top of the crater, at least that was for phase 1. Now phase 2, we are just worried about excavation and bringing it to the dump site. And we have made it to past the design portion, and we're now going to be into the build portion. And then we will do a 15-day durability test where we test our designs on a track just on the other side of town at a quarry. And we'll get into our design now.
All right, so we've got a little project overview here. So just kind of outlining some of the parts of our system that we have. So obviously our main focus is going to be on the excavator, and our main goal is mining that regolith. NASA is requiring 800 kilograms plus or minus 10% per day for 15 days. So that's our main goal. The dump truck's main goal is to transport that regolith from the excavation rover to the NASA provided dump site. Battery swapper is switching batteries on the excavator to make sure that we have as little downtime as possible. And the test track is going to be testing our robots to the specifications outlined by NASA to make them capable for the mission on the moon.
So the goals for this project include to develop and design an excavator. First of all, we want to prove that it's durable, reliable, and that it can maneuver on the lunar surface. And so like Tom and Brock talked about, our main goal that we have to do is we have to mine 800 kilograms plus or minus 10% each day. And then our test track goal was to make a test track that simulated the lunar surface. So our constraints, so for the delivery, like we talked about, we have to go from the excavation site where the excavator will be at to the dump site, and that's 500 meters or 545 yards away. An overall system weight goal or limit that we have to be less than is 10,000 kilograms or about 22,000 pounds on Earth. And then our total size, everything that we design and make and take to the moon has to be inside a 6 meter, which is about 19 and a half feet by a 10 meter long cylinder, which is 32 and 3/4 feet. So if you imagine a rocket, that's basically what we have to fit our designs into. So, and all these constraints and goals we had in mind while we were designing our final excavator. So that's what we're going to show you next.
Here's kind of the first view of our excavator here. We have what we ended last semester with in May here on the right, and then our final design there are on the left, and our final design here on the right. As you can see, they're visually different, but they both serve the same purpose. We have an excavation wheel here on the front and a conveying system that brings the mined regolith from the arm to the rear, where we will dump into a dump truck, and we'll get into the specifics of how everything works here shortly.
So to give you guys an idea of just how big this thing is, we added some overall dimensions. The overall length of the excavator is going to be around 15 feet. The overall width of the excavator is going to be around 6 feet, and it's going to be 5.5 feet tall. So those numbers probably don't mean a lot to you. So we compared it to a 2021 Honda Civic's LX CVT, and we found that our excavator is slightly larger than this car. The final weight of the excavator is going to be around 656 kilograms, which translates to 1,448 pounds.
So, and here's the test track. We were working with a limited space at the LG Everest quarry. They donated some space, but because of the constraints with that, we had to get a little creative with how it's all laid out. So over here on the left side, we're going to start with the excavation site, and then the dump truck and battery swappers have to travel all the way down and up and back across, going through very treacherous terrain like craters, over to the dump site and the battery swapping site. There's on the right side, in the blue, green, and red boxes, there is different sorts of terrains that get increasingly more difficult to travel. And those are scattered around the test track, as well as a 10% incline and 10% decline outlined by the yellow arrow. That's to simulate having to get out of a crater or some other treacherous terrain. This blue arrow on the right side over there is a very fine grit sand that is more applicable to the moon's lunar surface than playground sand would be, which is what we're using for most of it. But we can't afford moon sand, or at least not near as much as we would need. So we have a small patch of it just to prove that we can go through that and make it through it. And then on the next slide, this is our excavation site. If you'll imagine, we will dig out this whole area, fill it up with concrete that is very similar to the likeness of the moon's lunar rocky surface. And then we will start to dig down at a 5-degree incline until we get to about 60 centimeters down. Then we're going to go level out until we get about 15 cubic yards, which is around how much kilograms we need for the whole 15-day period. And yeah, that's it.
So this is a picture of a bucket wheel excavator. Bucket wheel excavators are used in large open pit mining operations to collect materials such as gravel and coal. These things are massive. They weigh around 14,000 tons. It can harvest 240,000 cubic meters of material a day. If you would like to purchase one, they only cost around $100 million. We obviously do not have that type of budget, so what we have designed is a much more compact and mobile version of this bucket wheel excavator.
So this is our prototype bucket wheel here. You can see it mining away. This is the actual exact material that we are planning on using for our 15-day test. So you can see the grinding nubs in the form of bolts there, and they are breaking up that surface. And then the plates come by and scoop up the broken up material. And Brock will highlight how we then capture and convey that scooped up material.
So our last year's testing was a simplified version of our final design, as you can see here on the right side of the screen. For grinding nubs, we are still using those bolt heads, and they're going to grind against that material, as you just saw in that video. And we also added grinding plates on the side of the bucket wheel excavator. And this is so when the arm is rotating left to right while we mine, we can be excavating that side area and not just having a flat plate rub against some soft concrete and do nothing. And then these opening slots there are those plates you saw in the last video where the regolith will fall into the center of the wheel, where the conveyor on the other side of the screen will carry it from the wheel to the cart that dumps into the dump truck. And we have a motor mounted on the top of the conveyor that drives the conveyor as well as the wheel using a chain system.
So this is the CAD model of our frame. Main things that we're seeing here are our drive motors to actually cause the vehicle to drive forwards and backwards. And then also the electrical compartment there. So that's going to house basically the brains of the motor, as well as the motor drivers and everything that we need to make it go. One thing to notice here is we have no suspension. This is for simplicity as well as basically just simplicity. Suspension gets weird on the moon and we are traveling at a very slow speed. So we had some advice that would just add unnecessary complexity. We're using a tank steering system. So basically one half of the excavator will drive a little bit faster than the other side in order for us to turn left and right.
And as I mentioned previously, the bucket wheel excavator will be sweeping from left to right, and we will be carving out a 2.2 meter path in front of us so we can drive into the hole that we create, as Dante showed in his graphic earlier. To do this left to right sweeping motion, we have designed a worm gear driven system as opposed to a 4-bar linkage system that we had designed last spring. We went with this system because it's more compact, simpler to manufacture, and we can shove it farther forward in our design, making our arm shorter, therefore lighter. And how the system works is we mount a motor to the shaft on the left side of the screen there, or the right side from your point of view. And as you spin the shaft, the big gear will rotate left or right, depending on which way we want to go. And when we hit our stop on either side, we will reverse the motor and swing the other way and carve that 2.2 meter path in front of us.
And this is our battery swapping situation here. There's actually a whole other sub team dedicated to the power delivery. So I'll make this one quick. But basically, there's an inlet for in the back of the excavator to receive a battery. There's an actuator which pushes the battery out onto the battery swapping rover that comes up on these ramps here. And then it will use that same actuator to pull the battery back in and lock it in and secure it.
So like Brock was talking about, this is the front arm circled in blue. That's how we'll be mining this regolith. And then the regolith will travel up that arm to a conveying system to our cart circled in orange. So this cart was based off of a roller coaster design or idea. So this cart will travel up this track here and pulled by a chain. And then once it reaches the end, it'll stop. And then this linear actuator will be tucked underneath here and will push up on the back of the bucket, causing it to tip. So like we talked about, there's a dump truck group, and the dump truck there is in that video. It's that little guy going up to our excavator. And that's how our cart will dump the material into the dump truck.
So here we've done some research on our wheels, and we found that rubber wheels cannot work in space. At around 70 degrees Fahrenheit below zero, rubber becomes very brittle and easy to break. And our excavator will be operated and tested at temperatures that can exceed 300 degrees Fahrenheit below zero. So what we've done is we've taken inspiration from the NASA's Volatile Investigating Polar Exploration Rover, also known as Viper, and we found that they used aluminum-based wheels. So that is what we have done with our wheels. So towards the left, you can see a topology study that we ran. Topology optimizes material layout. So what it does is you give it a blank slate of material like the one shown in the top left, and then you tell the computer, hey, I want you to take out 60% of the material from this object that I gave you. And then the computer will take out 60% of that material, and then will output the stiffest pattern possible at that reduced weight. So this picture helped us save 40 total pounds on the excavator. On the outer diameter, you can see we have settled on V-shaped gousers and acorn nuts to give us optimal traction in both soft regolith and the soft sand.
So here's our Gantt chart, kind of our schedule for the rest of the challenge here. We got to continue to order parts, and then we're going to build our wheels, build our frame, build the conveyor, build the whole system, and then test each subcomponent together, and then test the whole system as a whole. And then we'll get ready for the 15-day trial, and then we'll execute that.
For our budget, our frame made mostly of square aluminum tubing comes out to $5,000. Wheels and drive motors will cost us around $6,600. The wheels will cost end up costing around $500, which means we have $6,000 saved for motors. They're so expensive because we drastically overspec them to make sure that we can handle anything that the moon throws at us. The excavator arm and worm pivot joint will cost around $6,000. The conveyor cart and support will cost around $4,700. The dust covers will cost around $620. And finally, the electrical, which includes anything from sensors, controllers, wires, buck converters, will cost $3,000, which brings our total excavator budget to $26,166.96, or pretty much the cost of a Honda Civic. Any questions?
Will you be bearing any rocks in your concrete to do some tests with that?
I don't think so. The rules didn't really say anything about that. I think they want a pretty consistent concrete thing, I think. Pretty sure the rules want a consistent layout for the concrete, but I'm sure there are rocks buried underneath in the moon's surface, but that is not what we're testing here, which thankfully for us. Any other questions? Nick?
So the alignment system for the dump truck aligning with the excavator, does that alignment system raise and lower the slope you're on? I know it's taken down.
We'll get the picture up here. Yeah, so the ramp system, as you can see in the picture here and the video, is hanging by these chains, and those chains are controlled by an actuator. So we're gonna, on transport, like flying it to the moon, the ramp will be up, and then when we get to the excavation site, we can lower it down and it will ride on the surface. So it'll kind of free hang there. So we'll be at whatever we need, and the chains will have some slack in them. And then when we move, we can raise them up so that the ramp does not scrape against the surface.
Just looking at this animation, how much of that bucket are you going to be able to fill from that one end?
So are you asking like from the end of the excavator?
It
Or?
looks like the end of the dump bucket is really close to the edge
Right.
of the dump truck. Right?
So-
how is it going to fill the dump truck instead of just spilling over the edge?
Yep. So one thing we have missing from our design as a whole is some sort of, basically exactly what you're talking about, is some sort of funnel. And that was incorporated on our last semester's design. And we just have neglected to get one into this design. But our hope for that is to have some sort of system in there to disperse the regolith around so that it doesn't just mound up in the inside of the dump truck, and also get it out far enough so that it can hit in the center. Yeah, sorry, this is the funnel I was talking about. It's very hard to see what that actually looks like.
And then when you did the optimization on the wheels, what type of
So for the loading, I assumed a constant pressure around the entire outer rim to make sure that the wheel was equally as strong at any point. And then I fixed that center right here. And then I set up a constraint so it would save this inch of material to make sure that we can drill in and put our plates in, as you can see right here.
what size motor?
It's after we put it through a 200-to-1 gearbox, it will be around 1,400 Newton meters.
And you're not simulating any force.
Not during the topology, no. We did. I don't think it requires it.
1,400 meters is irrelevant.
Well, I made the topology and then I ran an FEA on it to make sure that it can handle the 1,400 Newton meters, and it passed with a factor of safety of about 1.4.
So what is the topology optimization?
It removed, it just took out material so we could save weight.
No, I understand that, but if it didn't consider the torque at all,
I didn't,
how would it have been different? If the torque were considered in that?
I never even considered that. I'll have to go back and see if it has any effect on it or not.
Don't know the friction coefficients yet for the wheel, which I think would be important, because you can't just fix the bottom of the wheel and slide.
No, but you got little bolts.
They're like
Little
8
knobs.
Yeah.
Bolts and whatever.
Yeah.
I mean, there's gonna be. You know, that gets hung up on something. I was just concerned that your optimization of the wheel didn't consider.
Yeah, now that you bring it up, I'll go back and make sure that it doesn't have any effect, or if it does, I'll go back and change the design.
We haven't cut those out yet anyway. We have just the big plates right now that are, it's only wheel around for the first prototype. Not too late. Good question.
How much assembly is required for this coming off the space back? Pretty much there, you put down the ramp and go.
That was the idea of the project, is to have this fully, or as little human involvement as possible. And so that's what we kept in mind when we were designing this. So yeah, obviously some of this would be a lot easier if a person could walk up to it and, you know, assemble this stuff and everything. But because it's going to the moon, and because you don't want astronauts, you know, hanging out in space for that long, we had to, you know, design it so that people wouldn't have to get involved with assembly.
This is our shipping configuration with the ramp up and the arm down like this. So the ramp is up so it can save space.
All these cycles do take out.
The bucket that dumps out. Yeah, I like that. Yeah, it'll be able to, we got to take it real slow and
Worst case scenario, we can just go straight, stop, and it doesn't have to be a fluid, you know, arching thing, especially dump truck. Dump truck is a little more, easier maneuverability with that. We can just drive another car in, but the dump truck would have to be more points.
So we're gonna use the hydrogen as fuel for a rocket to get to Mars. That's the main idea. They might have other purposes for this water, but as far as we understand, it's mainly they're gonna try and extract the hydrogen from the water and then use that as a fuel.
I think the slingshot around the moon.
We just don't want to be shipping water up there because every time we set up, we're going to pass so much money to them. More that we can just take and then cheaper for the.
Okay, any other questions?